couple things. First of all, you're going to need to do some reading, maybe some reviewing. Because if you look at page 80, 81 in your book, there's a couple theorems there for basic limits and limit laws. I'm not expecting you to memorize, like, what's the sum limit law, but what I am expecting you to know is how to use it. And most of you probably do. To be honest with you, a lot of these limit laws or properties, theorems, are kind of common sense, especially too if you have seen them. So it says, note that the limit laws for sum, difference, product, quotient of two functions, they only apply if the limits of both functions exist at the specified point. So once one of those limits doesn't exist, that overrides any value. Okay? So I think I have a problem in here that I do that kind of does that, so we're going to take a look at it. All right, so first of all, you have f of x and g of x defined by two specific graphs. This is our f of x graph right here, and this right here is our g of x graph. We don't have the function, but we have the graph, and we should be able to read that. We don't really care if we have the function or not. It doesn't matter. And what we're going to do is use these to help us evaluate specific sums, differences, quotients, products, etc. All right, so we're going to take a look at A. I'm not going to do every single problem here. The ones that I don't do, I'm recommending that you go back to, whether it's now or later, and complete them. So in A, it says we want to find the limit as x approaches 2 from the right of the sum of f of x and g of x. So by definition, the theorem basically states that you're going to evaluate the limit as x approaches 2 from the right of f of x, and evaluate the limit as x approaches 2 from the right of g of x, and then add the two together. I'm not expecting that you rewrite them. It's just that would take you forever. So here, if we just evaluate the limit as x approaches 2 from the right of f of x, what does that give me? -1, okay. Plus the limit as x approaches 2 from the right of g of x. From the right. It is 3. So then the limit overall is 2. You're done. So kind of common sense, right? You just evaluate. So here we have the limit as x approaches 2 from the left of the quotient of g of x over f of x. So let's take a look at g of x first. The limit as x approaches 2 from the left gives me what? 3? Okay. And then the limit as x approaches 2 from the left of f of x. It's also 3. So then the limit overall of the quotient as x approaches 2 from the left is 1. Questions? You guys good? Okay. Let's take a look. The limit as x approaches 2 overall of the product of f of x and g of x. All right, well, let's take a look at the limit as x approaches 2 of f of x. Tell me what you got here. Yeah, it doesn't exist. Okay, so just before, probably about, I don't know, 2 minutes ago, I said, as soon as you get DNE, that overrides anything else. So is it really even worth my time to evaluate the limit as x approaches 2 of g of x? Doesn't matter what the value is, it's still not going to exist because it's the product of the two. So the answer here does not exist. Okay? Questions? All right. Let's see. Let's take a look here. D. The limit as x approaches -3 from the right of the difference here. So let's take a look at the limit as x approaches -3 from the right of f of x. Where are we? We are -4. Minus the limit as x approaches -3 from the right. Okay, so this becomes positive. So what is this answer overall? -2? Okay. All right, the limit as x approaches -3 from the left of the product squared. So we're approaching -3 from the left of f of x. We're down here where? -4. Okay, so we've got -4 times, let's go over to g of x. As we approach -3 from the left, I heard it, -2. And we're going to square that. What does it give me? Yep, 64. Okay, up to this point, everybody okay? Pretty basic? Yep. All right, let's move a little bit. I'm going to skip F. We're going to take a look at G. We want to evaluate the limit as x approaches 3 of the square root of g of x. So ideally, this theorem says to evaluate the limit as x approaches a, in this case it's 3, of g of x, and then whatever that solution is, we'll take the square root. If it's something that you can simplify, like the square root of 4, you would simplify. If it's something like the square root of 8, you would write it as 2 square root of 2. If it's irrational and you can't simplify it at all, you just leave it. Okay, so the limit as x approaches 3 from both sides, because we're evaluating a limit overall of g of x. Okay, so here I'm approaching 3. Oh, what's my answer? 2. So this answer is just the square root of 2. Okay. Let's look at h. The limit as x approaches 0 from the left of g of x over f of x. So let's look at g of x first. We're approaching 0 from the left, 1, okay? And then what about f of x, 0 from the left? Oh, what is that? It is undefined, therefore the limit does not exist. Okay. Questions on using these properties? Anyone have any? No? Okay. So now we're actually going to go back and evaluate using some algebra. So we want to find these limits algebraically. And when you're asked to find the limits algebraically, basically what we're asking you to do is try direct substitution first. Okay? So we're going to look here at a direct substitution problem. The way I approach a direct substitution problem, or any limit problem at all, is I always try direct substitution. I look at the function that we're evaluating the limit as x approaches a, and I ask myself, first of all, is there any place that this function is undefined? First of all, can you classify this function for me? Yeah, it's a quadratic. What's the domain of a quadratic? All real numbers, negative infinity to positive infinity. So in plain English, that means it's not undefined anywhere, right? I could put any number in there, and it doesn't matter. It's still going to be defined. So that means if I use direct substitution, no matter what answer I get, it's on the number line somewhere. Agree? Decimal, negative, positive, 0. Okay, so let's just plug in. So we have 4 times 1 squared, which is 1, minus 10 times 1, which is 10, plus 3. So what does that give me? Negative 3. So in this case, evaluating the limit as x approaches 1 of f of x is basically the same as evaluating f of 1, right? Same thing. Okay, so you might actually be given a problem like this that says evaluate the limit as x approaches 1 from the right. If you're evaluating the limit as x approaches 1 from the right of a polynomial of any kind, and that's a very generic term, but meaning it's not undefined, the function that you're given, all you have to do is plug in the value. It doesn't matter if you're approaching from the left or from the right. Using 1 is a sufficient value, because if you're approaching 1 from the right, the best number to really use is going to be 1.000000001, or even more zeros than that, but you don't have a calculator. So why don't you just use 1? It's not undefined, just see what happens, right? Okay, questions? Okay, so here, if we try using direct substitution, so I'm going to do it up here, I'll just call it DS, direct substitution. I've got 1 squared, which is 1, minus 6 times 1, which is 6, plus 5, over 1 minus 1. What do I get here if I use direct substitution before doing anything else? 0 over 0. Okay, it's not just that it doesn't exist, I can't even evaluate that for multiple reasons. Number one, you can't divide by 0. Okay, so we know that's undefined, but nothing going into nothing, 0 going into 0. It's just like if you have infinity divided by infinity, well, first of all, infinity is not a number. Conceptually, you're saying that the behavior of the function in the numerator and the denominator are increasing forever, right? I didn't want to use infinitely because I'm using the same word. So this is known as an indeterminate form, okay, and it's 0 over 0 or infinity over infinity. And really what this is saying is you got to use a little bit more algebra so that we can use direct substitution. Okay, so there are certain things that we're going to have to do. Factoring, rationalizing, simplifying complex fractions. These are all common things that you've done in algebra and in pre-calc. and you're expected to kind of tap back into those memory banks and remember how to do it. So in this case, we're actually going to factor. So if you have not evaluated the limit, meaning you haven't used direct substitution, you have to carry the limit as x approaches a all the way through until you actually evaluate. If you do not, you're not evaluating the limit. You're not stating what you're doing. So I'll be honest with you, in this class, and when you sit for any exam, whether it's our test or if you do sit for the AP and it's a free response, if you don't write the limit as x approaches a until you actually use direct substitution, it's all incorrect, the whole thing. Okay? So make sure, I know it's annoying, you have to write it out, it's hurting my hand, I'm not used to it, so you just have to do it. Okay, so we've got the limit as x approaches 1 of my factors here in the numerator are what? X plus 6? Yeah, x minus 5 over x minus 1. We just have to be careful and make sure we multiply, because if it was x plus 6, then my product would be negative 6, but my product is 5. So I need to know what times what is positive 5, but when I add them I get negative 6. Okay, so now what that allows me to do is cancel those out, right? Okay, and I'm left with the limit as x approaches 1 of x minus 5. Okay, so now what we want to do is try direct substitution now, which means I'm going to plug in 1. 1 minus 5, negative 4. Not undefined, right? What is this called graphically? Yeah, it's a whole when you have a common factor in the top and in the bottom. Okay, so the limit as x approaches 1 of x minus 5 is negative 4. Okay, let me just show you something really quick. And I know some of you probably don't even care, but pretend like you do. 1, 2, 3, 4, 5. 1, 2. Okay, so in the case of my original function, this is going to be the graph right here. I have a hole at the point x equals 1 and y is negative 4. So it's like right here. Okay, so if I were to sketch this, even if I put this in the calculator actually factors it for you and cancels out the hole. But then when you go into the table, if you go to where x is equal to 1, there's going to be an error message. Okay, so what it would give you is something like this graph, and then when you go into the table, you would see that this function is undefined right here. Okay? So what's the limit as x approaches 1? Excuse me, yeah, 1. Still negative 4, right? Graphically, that's what we were just doing. So then if I were to graph x minus 5, that's just a linear function with an intercept here at negative 5, right? So this is approximately what the graph looks like. Don't they look the same? Only difference, what, the hole? But in this case, I don't really care about that. What I care about is the limit. Isn't the limit the same for both of these as x approaches 1? Yeah. You don't have to draw the graph, but this is just to show you. This is what happens when you cancel out the hole. Okay, so this is factoring. Okay, so for those of us that said, oh, I forget how to factor, or factoring wasn't my strong suit, we need to be good at factoring. Okay? All right.